Welcome back. We're now moving on to 11.2, electrolytes. In this section, we're going to define and give examples of electrolytes, distinguish between the physical and chemical changes that accompany dissolution of ionic and covalent electrolytes, and relate electrolyte strength to solute-solvent attractive forces. So let's first define electrolytes. These are substances that dissolve in water and undergo a physical or chemical change to produce ions. A non-electrolyte is a substance that does not produce ions when dissolved in water. For instance, sucrose that we looked at last section, it doesn't break apart into positive and negative ions, it stays together, but it still dissolves. So now electrolytes, you're probably already thinking things like ionic compounds, like that potassium dichromate and sodium chloride, and you are correct. Now we can classify electrolytes as either strong or weak. A strong electrolyte has basically 100% of the dissolved substance generates ions. So if you put sodium chloride in water, it basically all breaks up into sodium plus and chloride minus ions. But a weak electrolyte is when only a small fraction of the dissolved substance generates ions. So this could be something like acetic acid or vinegar. When you put it into water, only a little bit of it breaks apart. It's sometimes like 1% of the molecules are able to dissociate. So it's also, we call it partial dissociation. Okay, whereas the strong electrolytes have complete dissociation, they completely break apart. Now, what's really cool with electrolytes, and one way you can test if you have one, is if you have one of these apparatuses that has a light bulb and it's got a positive cathode and a negative anode, and you dip it into a solution. And if the bulb does not light up, then you have a non-electrolyte. So something like ethanol, there's no conductivity, there's no charges. If you were to dip it in something like aqueous potassium chloride, it would light up very, very bright because it has high conductivity. It's a strong electrolyte. So strong electrolytes would really just make that light bulb just woo. And now something like acetic acid, that is a weak electrolyte. When you stick the light bulb in, it'll turn on very, very dimly, but there is still some charge floating around in there. So what's kind of interesting, something to think about, is if you were to do this test with something like tap water, you might actually notice the light bulb turns on, albeit very, very dimly, almost hard to see. But it does turn on, indicate there's some positive, negative ions floating around. And this is a big wink wink because I think I might put this as an extra credit question on your final. The reason for this is because tap water tends to have a lot of ions and a lot of minerals dissolved in it. So maybe some calcium, possibly some sodium, some chloride from if they do any chlorination. So these very, very trace amounts of minerals. They're not bad for you, but they are there. Whereas if you did this test with something like pure water, deionized or distilled water, they shouldn't turn on because those ions have been removed. Something like salt water or ocean water is going to light up like a Christmas tree, okay, because it's got a ton of strong electrolytes in it. So it gets very, very bright. So let's talk about ionic electrolytes. So water and polar molecules, because of that separation of charge, are attracted to ions. So we can have this electrostatic attraction between an ion and a molecule that has a dipole in it, so a polar molecule, and this is called ion dipole attraction. So you have this full charge attracted to a partial charge, or the partial charge attracted to the full charge. So what happens is, for instance, with water, the water molecules are going to surround and solvate these separated ions. And we'll look at what that picture looks like on the next slide. And this is called dissociation, okay? So it goes and surrounds the separated ions and it keeps them from each other. It dissociates them. So this is what it looks like. For instance, the Cl- you see here, the hydrogens, which have those partial positive ends, are attracted to the chlorine, that negative charge. Whereas the oxygens that have the partial negative charge from water, the water orients itself depending on what ion that those water molecules are going to. In this case, now the oxygens with that partial negative are surrounding the positive charge of the potassium. So this is how the dissolution process happens. And you can also kind of see how this ends up being a spontaneous process, because one at a time, the water molecules are kind of going in here and pulling off ions. And so eventually they're going to get to a point where they pull every single one off and they've all been separated out. So there are competing forces that influence how soluble an ionic compound can be. That ion dipole attraction. So if this is the dominant force, then the compound it pulled into solution has a high water solubility. Something like sodium chloride is very soluble in water. Okay, the other force is the force of attraction between oppositely charged ions. So if this is the dominant force, then the compound tends to be undissolved in the solid state and have very low water solubility. So this is why when we looked at solubility tables, there are some ionic compounds that don't dissolve in water. They would precipitate out because those ions are just so strongly attracted to each other that the water molecules cannot pull them apart. And then we also have covalent electrolytes. And so these are made when a covalent compound is able to react with water to produce ions. So for instance, HCl, hydrogen chloride, when you put that into water, it breaks apart, it dissociates, and hydrogen goes to the water to make hydronium. And then we're left with this Cl minus. So we can see we've made a positive and negative charge. So good old acid-base chemistry. And this reaction actually with HCl is basically 100% complete. So HCl is a strong acid and it's also a strong electrolyte. So if you have a weak acid or a weak base, these are going to be weak electrolytes. Strong acid, strong base, strong electrolyte. So a strong acid or base equals strong electrolyte. Whereas if you have a weak acid or base, I'm just going to put A, B, then you have a weak electrolyte.